Okay, so let me ask you a question. Imagine an 8 by 8 chessboard. You know the one, 64 squares, alternating light and dark. Now, here's the puzzle. I want you to place 8 queens on this board, but here's the catch. No two queens can attack each other. Not in the same row, not in the same column, and not even on the same diagonal. So, the question is, how on earth do we find such an arrangement? And how many even exist? That's exactly what we're going to figure out together. First, a quick reminder of how the queen moves. If a queen sits on this square, she can move horizontally, vertically, and diagonally in all 8 directions. So this is what she attacks, every square along those 8 rays. Which means if any other queen lands on one of these squares, we've got a conflict. And that's exactly what we're trying to avoid. Place n queens, none of them sharing a ray. That's the whole puzzle.
All right, let's start small. 4 queens, 4 by 4 board. This is the warm-up. Can you place 4 queens here with no 2 attacking? Take a second, think about it. Try the obvious thing. Put one in the corner. Now where can the second one go? Not on the top row, not on the leftmost column, not on the diagonal. So it has to be over here somewhere. How about there? But actually that's going to dead end pretty quick. Let me just show you a real solution. 1 queen here, another there, 3rd in the corner, and the 4th right there. 4 queens, no conflicts. And believe it or not, there are only 2 solutions for 4 queens. Just 2.
Okay, so how do you find a solution with a computer? The simplest idea? Brute force. Try every possible arrangement of queens, and for each one, check if it's valid. For our 4 by 4 board, that's 16 squares, choose 4. 1,820 combinations. Manageable. We could check them all by lunch. But for 8 queens, now we've got 64 squares, choose 8. That's about 4 billion. 4 billion. And honestly, that's the dumb brute force. You can shrink it down a bit by saying put exactly 1 queen per row, which gives you 8 to the 8th, around 16 million. Still way too many. We need to be a lot smarter. So here's the smart approach. It's called backtracking. The idea is, instead of testing entire boards, we build the solution 1 row at a time. Place a queen somewhere in row 1, then try to place a queen in row 2, but only on a square that doesn't conflict. Then row 3, then row 4, and here's the key bit. If at any point we can't place a queen, we go back. We undo the last queen and try a different column. That's the backtrack. The huge win is, the moment we hit a dead end, we stop. We don't keep filling in queens on a board we already know is doomed.
Okay, so let me lay out the approach in plain steps. Step 1, we pick a row and try each column in turn. Step 2, for the square we're trying, we ask, is it attacked by any queen we've already placed? Step 3, if it's safe, we place a queen there. Step 4, we move on to the next row and do the same thing. Step 5, and this is the key part. If at any row we run out of safe columns, we undo our last placement and try the next column. That's the backtrack. And step 6, when we filled all n rows, we've got a solution. Now watch the same 6 steps run on the board. Row 0, first column, place. Move to row 1, column 0, same column as our queen, attacked. Column 1, on the diagonal, attacked. Column 2, safe, place. Row 2, every column in row 2 conflicts with one of the queens above, dead end. We undo. Try column 4, place. Row 2 again, column 2 is safe, place. Row 3, no safe column, undo. Row 2 is also out of options, undo again. All the way back to row 0, move the first queen 1 column right. Now things flow. Row 1, safe column. Row 2, safe column. Row 3, 4 queens placed. Solution. All 6 steps. No code, just the idea.
Now scale this up. 8 queens. Same algorithm, row by row, undo on conflict. I'll fast forward through the search and just show you the queens landing in their final positions. And there it is. 8 queens, 0 conflicts. One of 92 distinct solutions for 8 queens. And the algorithm probably checked a few 100,000 partial boards to get here, versus 4 billion for brute force. so vastly better. Same idea, backtracking, but a real production-grade speedup.
All right, now if you want to go really fast, there's one more trick. It's called bit masks. And again, I'm not going to show code. I want to show you the idea. Step 1. Instead of remembering which queens went where, we just track 3 things: which columns are already taken, which falling diagonals are taken, and which rising diagonals are taken. Step 2. Each of these 3 things is stored as a single integer. Bit 0 is column 0, bit 1 is column 1, and so on. A 1 means taken, a 0 means free. Step 3. To find the safe squares in a row, we just OR those 3 integers together. The bits that are still 0, those are the safe columns. Step 4, and this is the magic. That whole conflict check is one CPU instruction. No loops, no nested if statements. Step 5, same backtracking algorithm as before, same big O, but the inner loop runs maybe 10 times faster because conflict checking went from a loop to a single bitwise operation. For competitive programming, that constant factor speedup is the difference between passing the time limit and getting TLE'd.
So there it is, 3 approaches to the same problem. Brute force, slow, but the code is 5 lines and you write it without thinking. Backtracking, fast enough for any reasonable n, and the one you'd actually use in real life. Bitmask backtracking, fastest, slightly trickier code, mainly useful when you're squeezing every millisecond. Same problem, same answer, n queens. And that's pretty much the whole story. Thanks for watching.